This is SpaceTime Series 29, Episode 25, for broadcast on the 27th of February 2026. Coming up on SpaceTime, mysterious gullies on the red planet Mars that appear to have been dug, the discovery of a unique inside-out planetary system, and Europe's most powerful rocket undertakes its first launch. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have been studying a set of mysterious gullies on the red planet Mars that appear to have been excavated, raising questions of how. Now, a report in the journal Geophysical Research Letters has determined the likely culprits aren't Martians, but rather blocks of frozen carbon dioxide. The study's lead author, Reneke Rolos from Utrecht University, says her tests showed how these blocks of CO2 ice were able to dig gullies in a unique way. She says she felt like she was watching the sandworms in the movie Dune. Now, other researchers had previously suspected that these blocks could play a role in the formation of the gullies. But this is the first work to actually prove it. It's a phenomenon not seen on Earth and has never been observed by anyone previously. It works like this. Ice forms in the Martian southern hemisphere desert dunes during the winter. That's when temperatures can drop to minus 120 degrees Celsius. At this time, a layer of CO2 ice forms over the entire surface of the dune field, sometimes up to 70 centimetres thick. Then at the end of winter, the dune slopes heat up and blocks of ice break off, some of which up to a metre long. Now, due to the thin Martian atmosphere and the large temperature differences between the warm dune sand and the ice, the bottom of the ice immediately turns into a gas, a process called sublimation. Now, as a kilo of gas requires more space than the same weight of ice, the gas pressure blasts away the sand around the block, causing the block itself to dig into the slope, and it becomes trapped in a hollow surrounded by small ridges of settled sand. However, the sublimation process continues, and so the sand keeps on being blasted away in all directions. As a result, the block gradually moves downhill, leaving a long, deep gully behind it with small sand ridges on either side. Once the block reaches the bottom of the slope and stops moving, the ice continues to sublimate until eventually all the CO2's evaporated. And so all that remains is a hollow in the sand at the bottom of the dune. This is SpaceTime. Still to come, discoveries of a unique inside-out planetary system, and Europe launches its most powerful ever rocket for the first time. All that and more still to come on SpaceTime. Astronomers have discovered a distant planetary system that's turned scientists' understanding of planetary formation inside out. Our Sun's planetary system consists of 4 inner terrestrial rocky worlds, Mercury, Venus, Earth and Mars, followed by the gas giants, Jupiter, Saturn, Uranus and Neptune. But this newly observed system, catalogued as LHS 1903, is inside out, with a distant small rocky planet orbiting outside of 2 gas giants. Now, a 4th planet in the system does orbit closer to the host star than the big gas worlds, but it's still all very strange. The star LHS 1903 is a spectral type M red dwarf located about 116 light-years away. Traditional planetary system models, based on our own solar system obviously, suggest that the closest planets to their host stars are rocky worlds because stellar radiation sweeps away their gaseous atmospheres, leaving behind just dense rocky cores. As for the gas giants, they form further out in the cooler regions where gas can accumulate, and so planets there can hold on to their extended atmospheres. Yet the new findings, reported in the journal Science, show this distant rocky world orbiting LHS 1903, which appears to have either lost its gaseous atmosphere or never formed one in the first place. Astronomers made their discovery in data from ESA's Cheops characterizing exoplanet satellite. The study's lead author, Thomas Wilson from the University of Warwick, says this strange object makes it a unique inside-out system. Rocky planets usually don't form far away from their home star beyond the gas giants. So, Wilson and colleagues have set out to explore various possible explanations for how this rogue rocky planet could have formed. Could the rocky planet have simply been flung out there through gravitational perturbations? Or did it lose its atmosphere in some cataclysmic collision? After careful consideration, the authors eventually ruled out both these hypotheses. Instead, they found evidence that these 4 planets didn't all form at the same time as one would expect, but formed one after the other in a process called inside-out planetary formation. If LHS 1903 gave birth to its 4 planets one after the other, from the inner to the outermost planet, then each planet evolves in turn, sweeping up nearby gas and dust and leaving further out planets to wait and potentially evolve in a different environment. Wilson says this means that by the time the final outer planet formed, the system may simply have already run out of gas, which is considered vital for planetary formation. Yet here it is, a small rocky world defying explanations. He says it seems that we've found the first evidence of a planet that's formed in a gas-depleted environment. So this small rocky outer planet may simply be an odd exception, or it may be the first clue of a new pattern of how planetary systems can evolve. Either way, it's a discovery begging for an explanation that lies beyond science's typical understanding of planetary formation. This is SpaceTime. Still to come, Europe's most powerful rocket undertakes its first launch, and the March equinox, the constellations of Taurus the Bull and Leo the Lion, and 3.14159 Pi Day are among the highlights of the March night skies on Skywatch. This episode of SpaceTime is brought to you by Squarespace, the platform that makes building an incredible online presence not just possible, but effortless. I guess you could think of Squarespace sort of like a tidy roommate for your business. It handles all the scheduling crumbs, the unpaid invoices under the couch, and actually answers the door when customers knock. If you offer services, consulting, classes, events, whatever you call your expertise, Squarespace makes booking and getting paid straightforward. Built-in appointment scheduling, professional invoices, and secure online payments means you can spend less time juggling spreadsheets and more time doing what you love. And yes, people will actually find you. Squarespace's built-in SEO tools, that's meta description, auto sitemaps, and clean structure, help your site show up where it matters. So why not try it for free at squarespace.com/spacetime. And when you're ready to launch, use the offer code SpaceTime to save 10% off your first purchase of a website or domain. That's squarespace.com/spacetime and the promo code SpaceTime. And remember, you'll find the links in our show notes. Arianespace is undertaking the inaugural launch of the new Ariane 6-4, Europe's most powerful ever rocket. Mission VA-267 from the European Space Agency's Kourou spaceport in French Guiana carried 32 satellites into orbit for the Amazon LEO network, which aims to eventually rival Elon Musk's Starlink. It's the largest number of satellites ever carried by an Ariane rocket. And to carry such a massive load, the Ariane 6 was fitted with 4 strap-on solid rocket boosters rather than the 2 used on the 6 previous flights of the new launch vehicle. Amazon now has 175 broadband satellites in orbit, with plans to eventually expand the constellation to some 3,200. Now, rival Starlink already has 9,400 satellites orbiting the planet. After its initial launch in 2024, the new Ariane 6 rocket undertook 5 flights last year. Arianespace and the European Space Agency eventually plan to have Ariane 6 undertake an average of 10 launches a year. This is SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for March on Skywatch. Happy New Year! Well, it would be if this was ancient Mesopotamia or Rome. That's because March was the first month of the new year, going back to the earliest concept of celebrating New Year's Day at the time of the vernal equinox, around 2000 BCE. See, the ancient Roman calendar, which had just 10 months, designated March 1st as the new year. That 10-month calendar is still reflected today, with the name September or Septem being Latin for 7, October or Octo meaning 8, November or Novem 9, and December or Deci meaning 10. It wasn't really until the Gregorian calendar that January 1st marked the start of the new year. But in the beginning it was mostly Catholic countries that adopted it. Protestant nations only gradually moved across. with the British, for example, not adopting the reformed calendar until 1752. Prior to that date, the British Empire and its American colonies still celebrated New Year's Day on March 25th. The highlight of the month is the March equinox, which will take place at 1:46 in the morning of Saturday, March the 21st, Australian Eastern Daylight Time. That's 10:46 in the morning of Friday, March the 20th, US Eastern Daylight Time, and 2:46 in the afternoon, Greenwich Mean Time. For our listeners in the Northern Hemisphere, it means the vernal equinox, the start of spring, while those south of the equator, it's the autumnal equinox, meaning a move into autumn. The day marks the point in Earth's orbit around the Sun when the planet's rotational axis means the Sun will appear to rise exactly due east and set exactly due west to someone standing on the equator. It means almost equal hours of darkness and light. In fact, the very word equinox is derived from the Latin, meaning equus or equal, and nox meaning night. It all comes about because Earth's rotational axis is tilted at an angle of around 23.4 degrees in relation to the ecliptic, the plane created by Earth's orbit around the Sun. That axial tilt is always pointed at the same position in the sky, regardless of Earth's orbital position around the Sun. So, on any other day of the year, either the northern or southern hemisphere is tilted more towards the Sun. But on the two equinoxes, usually around March 21st and September 23rd each year, the tilt of Earth's axis is directly perpendicular to the Sun's rays. However, there's a complication called precession. This causes Earth's spin axis to wobble ever so slightly, just like the axle of a spinning top. The rate of precession is only about half a degree per century, so people don't notice it on human timescales. And because the direction of Earth's axis of rotation determines at which point in Earth's orbit the seasons occur, precession will cause a particular season, for example the Southern Hemisphere autumn, to occur at a slightly different place from year to year over a 21,000-year cycle. At the same time, Earth's orbit itself is subjected to small changes called perturbations. See, Earth's orbit's an ellipse, and there's a slow change in its orientation which gradually shifts the point of perihelion, Earth's closest orbital position to the Sun. Now, these two effects, the precession of the axis of rotation and the change in the orbit's orientation, work together to shift the seasons with respect to perihelion. And because we use a calendar year that's aligned to the occurrence of the seasons, the date of perihelion gradually regresses through a 21,000-year cycle. And there's another complication. Australia and some of the other Commonwealth countries start their seasons on the first day of the month, what are referred to as meteorological seasons, rather than on the solstices and equinoxes, which are referred to as astronomical seasons. So that means Australia's autumn officially began on March 1st rather than on the day of the March equinox. Meteorological seasons are used because it makes it easier for meteorologists and climatologists to break the seasons down into more exact 3-month calendar groupings for comparing seasonal and monthly statistics. The moment of the March equinox is also important in astronomy because it's used to define the celestial coordinate system of right ascension and declination. In astronomy, the celestial coordinate system is the astronomical equivalent to the latitude and longitudinal coordinates used on Earth's surface. It's used to specify the position of objects in three-dimensional space and the direction of those objects on the celestial sphere, the imaginary globe surrounding the Earth. In other words, it lets scientists determine the position of a celestial object, such as a satellite, a planet, stars, galaxies, and so on. Right ascension, which uses the symbol alpha, is the angular distance measured eastwards along the celestial equator from the vernal equinox. On the celestial sphere, it's analogous to terrestrial longitude. Declination, which uses the symbol delta, measures the angle north or south of the celestial equator, and so it's the celestial equivalent to terrestrial latitude. Marking the vernal equinox and setting the western evening sky this time of year is one of the oldest recognized constellations in the heavens, Taurus the Bull, so named around 6,000 years ago. In Greek mythology, Taurus represents the king of the gods, Zeus. Zeus lusted after King Agenor's daughter Europa, who was looking after a herd of cattle. Now, being a god and with godlike powers, Zeus decided to transform himself into a powerful white bull so that he could get closer to the beautiful Europa. Now, once transformed into a bull, Zeus convinced Europa to climb on his back, and he then carried her off to the island of Crete. Taurus's head is represented by a dominant V-shaped grouping of stars. The bright reddish star in the group is Aldebaran, an orange giant 1.5 times the mass of the Sun, located 65 light-years away. A light-year is about 10 trillion kilometres. The distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Aldebaran is the 14th brightest star in the night sky and the closest bright star to the point of the vernal equinox. In ancient Arabic, Aldebaran's name means the follower, as it appears to follow the 7 sisters of the Pleiades. It's also the first of the 4 royal or guardian stars identified by the ancient Mesopotamians. Now, that V-shaped grouping of stars near Aldebaran is known as the Hyades. It's the nearest young open star cluster to Earth, located just 153 light-years away. Between Aldebaran and the Orion constellation, you'll see a bright red star. That's Betelgeuse, the 9th brightest star in the night sky, these days more commonly called Betelgeuse. If you turn to the north now, you'll see the 2 bright stars Pollux and Castor, which represent the northern constellation of Gemini, the twins. In Greek mythology, they were brothers who travelled with Jason aboard the ship Argo in search of the Golden Fleece. Pollux is an orange-hued evolved giant star, located 34 light-years away. It has about twice the Sun's mass and is bloated out to around 11 times the Sun's diameter. In 2006, an extrasolar planet or exoplanet, designated Pollux b, was discovered orbiting the star. The planet is a gas giant, orbiting its host star every 1.61 Earth-years. The other star, Castor, is located some 51 light-years away, and it's actually a system of 6 stars comprising 3 eclipsing binaries. Eclipsing binaries are binary star systems in which the orbital plane of the 2 stars in the system lies so nearly along the line of sight from the observer here on Earth that the stars appear to eclipse each other. Looking to the northeast now, and you'll see the star Regulus, or Little King, the brightest star in the constellation Leo the Lion. Leo is mentioned by Homer in his famous 8th century BCE poem, the Odyssey. According to Greek mythology, Leo was killed by Hercules as the first of his 12 labours. Located some 79 light-years away, Regulus is a multiple star system composed of at least 4 stars. Regulus A, designated Alpha Leonis, is a spectroscopic binary comprising a rapidly spinning spectral type B blue-white star, around 3.5 times more massive than the Sun, with some 288 times the Sun's luminosity, and a small companion star, most likely a white dwarf, the stellar corpse of what once would have been a Sun-like star. The pair take about 40 days to orbit each other. Spectroscopic binaries are double star systems orbiting each other so closely and at such an angle that they can only be visually separated, from our viewpoint here on Earth at least, by their spectroscopic signatures. Astronomers describe stars in terms of spectral types. It's a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, then spectral type G yellow stars. That's where our Sun fits in. Then there's spectral type K orange stars, and the coolest and least massive of all stars are spectral type M red stars, commonly referred to as red dwarfs. Each spectral classification system is further subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest. And then you add a Roman numeral to represent luminosity. So, our Sun technically is a G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were born as spectral type M red dwarf stars but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a unique category between the largest planets, which can have around 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are around 75 to 80 times the mass of Jupiter, or about 0.08 solar masses. The primary star in Alpha Leonis completes a full rotation around its axis in under 16 hours. That's incredibly quick, especially when compared to our Sun's 30-day rotational period. Now, this gives the primary star an oblate appearance, and it causes what's known as gravity darkening, meaning its poles are considerably hotter and 5 times brighter per unit surface area than its equatorial region. Scientists estimate that if it were rotating just 15% faster, the star's gravity would be insufficient to hold it together, and it would literally spin itself apart. Located further away are Regulus B, C and D, which are all dim main sequence stars. Main sequence stars are those undergoing hydrogen fusion into helium in their core, like the Sun's currently doing. Regulus B and C are thought to orbit each other every 600 Earth years and are located around 5,000 astronomical units away from Regulus A. An astronomical unit is the average distance between the Earth and the Sun, around 150 million kilometres or 8.3 light minutes. Regulus B is a spectral type F white-yellow star, while its companion Regulus C is a small spectral type M red dwarf star. Regulus D is a bit more of a question mark. It's a dim star, and, at least from our point of view, it appears to be sharing motion across the sky with other members in the group. At the opposite end of the constellation of Regulus is the star Beta Leonis, or Denebula, the horse's tail. It's a luminous white star thought to be spectral type A, about half as bright as Regulus, and the third brightest star in the constellation Leo. Beta Leonis has about 1.8 times the mass of the Sun and about 15 times the Sun's luminosity. It's suspected of being a dwarf Cepheid or Eta Scuti type variable star, meaning its luminosity varies very slightly over a period of several hours due to pulsations on its surface. Also at the other end of Leo are the stars Theta and Iota Leonis, the loins of the lion. Theta Leonis is about 165 light-years away. It's a very young spectral type A white star, about 2.5 times the mass of the Sun. With an age of just 550 million years, Theta Leonis' spectra shows enhanced absorption lines for metals, that is, elements other than hydrogen and helium. This increased metallicity appears around 12% higher than the Sun, allowing the star to radiate with some 141 times the luminosity of the Sun from its outer atmosphere, at an effective temperature of 9,350 Kelvin, literally giving it a white-hot glow. Located some 79 light-years away, Iota Leonis is another spectroscopic binary, consisting of two stars orbiting each other every 183 Earth years. The primary star is a spectral type F yellow dwarf star, a little hotter and more massive than the Sun. Algebra, or Gamma Leonis, is a binary star system with a visible third component. The two primary stars are located 126 light-years away and can be resolved in a backyard telescope. Both are yellow giants, orbiting each other every 600 Earth days. The unrelated tertiary star, named 40 Leonis, is a yellow tinged star which can be seen through binoculars. Its traditional name, Algebra, means the forehead. Other stars in the system include Delta Leonis, or Zosma, which is a blue-white star 58 light-years from Earth, Epsilon Leonis, a yellow giant some 251 light-years from Earth, and Zeta Leonis, an optical triple star. The brightest component is a white giant about 260 light-years from Earth, while the second brightest star, 39 Leonis, is widely spaced and is located to the south of the primary, with the third and faintest star in the system, 35 Leonis, located to the north. Also located in Leo is Tau Leonis, visible as a double star through binoculars. It includes a yellow giant located some 621 light-years from Earth, and a binary secondary star 54 Leonis, a pair of blue-white stars divisible in small telescopes and located 289 light-years from Earth. Also in the constellation Leo, you'll find the Leo triplet, a group of 3 galaxies, Messier 65, Messier 66 and NGC 3628, all appearing relatively close together. Messier 65, also known as NGC 3623, is an intermediate spiral, possibly barred spiral galaxy, about 37 million light-years away. M65 disk appears to be slightly warped, and a relatively recent burst of star formation is suggestive of some gravitational interaction with the other 2 galaxies in the Leo triplet, possibly around 800 million years ago. Nearby is Messier 66, or NGC 3627, another intermediate spiral galaxy, some 95,000 light-years wide and about 36 million light-years away. Gravitational interaction from its past encounters with the neighbouring galaxies in the triplet has resulted in an extremely high central mass concentration, a high molecular to atomic mass ratio, and a resolved non-rotating clump of neutral atomic hydrogen apparently removed from one of its spiral arms. The third member in the group is NGC 3628, the Hamburger Galaxy, a spiral galaxy with a spectacular 300,000 light-year long tidal trail of gas and stars. NGC 3628 is located 35 million light-years away. Its most conspicuous feature is the broad and obscuring band of dust located along the outer edge of its spiral arms, effectively transecting the galaxy to the view from Earth. Other bright, well-known galaxies in Leo include Messier 95, Messier 96, Messier 105, and NGC 2903. M95 and M96 are both spiral galaxies, each about 20 million light-years from Earth. M95 is a barred spiral. Another barred spiral galaxy is NGC 2903, which is thought to be very similar in size and structure to our own Milky Way galaxy. It was discovered by William Herschel in 1784. Close to the M95-M96 pair is the elliptical galaxy M105, which is also around 20 million light-years from Earth. Okay, let's turn to the east now and the constellation of Corvus the Crow. In Greek mythology, Corvus was a really clever crow. In fact, he could talk to people. However, after refusing to speak to the god Apollo, he was banished to the sky, together with Crater the Cup and Hydra the Snake. One of the brightest stars in Hydra is Alpha, the solitary one, so named because it appears all alone in the sky. Okay, turning to the western horizon now, and you'll see the star Achernar in the southern tip of the constellation Eridanus the River. Eridanus is one of the largest and longest constellations in the sky. Achernar means the river's end, as it marks the end of the river Eridanus. Located around 139 light-years away, Achernar is a binary star system, comprising two stars, Alpha Eridani A and Alpha Eridani B. One of the 10 apparent brightest stars in the night sky, Alpha Eridani A is a young, hot spectral type B blue star, about 6.7 times the mass of the Sun, with a stunning 3,150 times the Sun's luminosity. Achenar's extremely high rotational velocity of over 16 km per second gives it an oblate shape, making it one of the least spherical stars in the Milky Way, with an equatorial diameter some 56% greater than its polar diameter. This distorted shape means the star displays significant latitudinal temperature variations, with its polar temperature being above 20,000 Kelvin, while its equatorial temperature, being much further away from the stellar core, is only around 10,000 Kelvin. Those high polar temperatures are generating a fast polar wind, ejecting matter from the star and generating a polar envelope of hot gas and plasma. The companion star, Alpha Eridani B, appears to be a spectral type A white star with about twice the mass of the Sun. The two stars orbit each other at an average distance of roughly 12.3 astronomical units. Now, just a quick reminder that March 14th marks the yearly celebration of the mathematical constant pi. Pi is the ratio of a circle's circumference to its diameter. But it's also an irrational number, meaning its decimal representation never ends and never repeats. More than just a number, pi has important applications in astrophysics, orbital mechanics, and other fields of astronomy. It's been calculated to over 1 trillion digits, and the current record for reciting pi from memory is over 70,000 digits. Imagine sitting next to that person at a dinner party. As for me, 3.14159 is about it. Of course, as well as Pi Day, March 14 is also the birthday of the great Professor Dr. Albert Einstein. And joining us now for the rest of our tour of the March night skies is senior science writer and Sky and Telescope magazine contributor Jonathan Nally.
G'day, Stuart. Yep, March night sky. Now, we normally start our tour of the night sky by looking to the south, but this time I thought we'd start with a view to the north, at least as we see it from down here where I live, within the mid-latitudes in the southern hemisphere. So as I look to the north during March evenings, low down in the northern sky, we've got 4 constellations in the zodiac. We've got Taurus, Gemini, Cancer, and Leo. Famous constellations. Cancer and Leo, they're a bit bare for the naked eye stargazer, not a lot to see. But Gemini and Taurus, these ones are really, really good, great constellations, primarily because they've got a couple of really, really good, or at least Taurus has a couple of really, really good star clusters in it. So in Taurus, you've got one called the Hyades, which is a V-shaped or wedge-shaped group of stars, quite large. It's really quite noticeable. It stands out. And there's another one that's a little way away, and it's smaller, but quite stunning. It's called the Pleiades, or the Seven Sisters, which we've spoken about many, many times on the program. That one I first mentioned, the Hyades cluster, it has a fairly bright reddish, really dark reddish sort of star at its head. And that's the star called Aldebaran, or Aldebaran as some people call it. That's in Taurus. In Gemini also does have some nice star clusters, but you really need a pair of binoculars to get a good view of those at least, and a telescope even better. But you can always tell the constellation Gemini because it has two bright stars quite close together. And they're both pretty much the same brightness as well. One's called Castor and one is called Pollux, which is, two bright stars close together, similar brightness. Obviously, it's Gemini, the twins. So still in the north, for us in the southern hemisphere at least, but higher up than those zodiac constellations, we've got the mighty Orion, which is one of the best known of all the constellations. Of course, we talk about it all the time on the show. Grab the chance to see it now during March because a couple of months' time it will have dropped below the western horizon and we won't see it again until the end of the year. This is the thing with constellations, they're seasonal because for us at this time of year, when it's night time, we're looking in one particular direction in space, out into space, right? 6 months from now, we'll be around the other side of the sun, and the night time there will be looking in the opposite direction, out into space. So as months go by, constellations drop below the western horizon, they come up in the east, and they just go through this repeating pattern every year. So Orion and these sort of ones, grab the chance to see them now before the weather, well, we're heading into winter down here in the south, so before the weather gets bad, and then we get lots of cloudy weather and you can't see anything. So, yeah, in other words, look at it now because it's going to be gone in a couple of months' time. Now, high overhead for us in the south, at least, we've got the two brightest stars in the night sky. We've got Sirius and Canopus. Sirius is actually a binary star system. It's made up of two stars, one a really bright one and the other one you can't see. So the larger of its two stars is about twice as massive as the sun, very, very bright, and the other one is a very tiny, unseen white dwarf star. You've got no hope of seeing it. It's really small, very close to its primary star and just gets drowned out by the light of the main star in Sirius. Now, Sirius is about twice as bright as Canopus as we see them in the night sky, even though Canopus itself, the second brightest star in the night sky, is 4 times as massive as Sirius, and intrinsically, it's much, much brighter. It's a brighter star, but it seems dimmer because it's a lot further away. Canopus is 310 light years from Earth, whereas Sirius is very nearby at only about 8.5 light years. So if you put Sirius at the same distance as Canopus, it'd be a nothing sort of star, and Canopus would be the brightest. So this is the thing you need to sort of remember when you're looking up there in the night sky and see all these stars, and think some are bright and some are dim. Some are bright because they are intrinsically bright, but sometimes it's just because they're close. And stars that are dim may be actually really bright stars, but they're just a long way away. That's the way things go. Now, sweeping south along the Milky Way, past Sirius and Canopus, we come to the far southern constellations, such as the Southern Cross or Crux or Crux, as I'm told it should be properly pronounced in Latin, and another one called Carina, which is a really great constellation to see down there. Lots of great stuff to see with a pair of binoculars. The Southern Cross is hard to see at the beginning of the year, sort of the end of the year and the beginning of the year, but by March, it's actually quite easy to see. As the months go on, the Earth is rotating. The Southern Cross, which during the end of the year period is way down on the southern horizon and is often below the horizon for many stargazers, it's now up a bit higher. So you should be able to see it no matter what. Just remember that at this time of year, it's on its left-hand side, sort of kite shape, right? So imagine a kite lying on its left-hand side and probably about a third of the way up from the horizon. That's in the mid-evening at least. Now, if you're up past midnight, then the Earth will have turned a bit more and therefore the Southern Cross will have risen higher in the sky and you'll see it standing much higher and standing straight up, which is the way most people imagine it to be. Now, let's turn to the planets. What have we got? As the evening falls, as this darkness starts to fall this month, only 2 of the planets visible to the naked eye are up and visible, and one of them won't be visible for very long, and that one is Saturn. In the first week of the month, you might just be able to see it as a pinprick of light in the twilight glow out to the west after the sun has set. It'll be in the orange glow of sunset after the sun has gone down. But by about the second week of March, it will be lost in the sun's glare. It's going to be around the other side of the sun, and we won't see it for a while. On the other hand, perfectly visible is Jupiter, the biggest planet in the solar system, and you'll see this one about halfway up from the northern horizon, for those where I live in mid-latitudes in southern hemisphere, or it'll be to the south, directly to the south, if you live in a country north of the equator. Now, Jupiter is pretty hard to miss, because apart from the moon, it's the brightest thing in the late evening sky at this time of the year. Now, I specify late evening sky because there is a third planet that's about to make its appearance, the one that's even brighter than Jupiter, and that's Venus. Now, I mentioned Saturn before and that it's going to be visible in the first week or so, the tiny pinprick of light in the western twilight glow. Well, as it disappears, Venus will appear up above the horizon in the west in that sort of glowing orange twilight. And it'll poke its head up and it's basically stay there hugging the horizon for all the rest of the month. So you should be able to see it because Venus is really big and bright. So even though it's in the glare, if you like, of the twilight glow, because it's so big and bright, you should be able to see it. Now, switching to the hours before sunrise, if you're up early or you're up very, very late, if you take a look into the dawn glow this time before the sun peeks up over the horizon, you should see what looks like a small reddish star. Well, that's the planet Mars. And just like Venus, Mars is going to hug the eastern horizon before sunrise for the rest of this month. So you should be able to see it at roughly the same, what astronomers call altitude, about distance above the horizon for most of the month. Now, if you keep watch, if you're up early, 6 o'clock or whatever, you're up early and you're watching before the sunrise, in the second half of the month, you'll see the planet Mercury. Day by day, it'll just zip higher and higher and higher in the sky, and it'll be very easy to see. Mercury is one of those planets, actually, that very often is hard to see because of the way angles and things work out between the Earth's orbit and the planet's orbits and what time of year it is and everything. Sometimes, even though Mercury might be at its greatest distance away from the sun as seen in the sky, what astronomers call elongation, and therefore you think, if it's a fairly long way away from the sun as seen in the sky, then should be easy to see, but sometimes no. Even though it can have a large elongation, it can be angled down towards the horizon, so it never rises very high those times, but this time it's going to come up sort of straight up and it's going to be very, very easy to see. The last thing for March, Stuart, is that, of course, this time of year, it's the equinox. So the equinox is going to happen on the 21st of March here where I am in Australia. In some parts of the world, it'll still be the 20th of March, depending on what your time zone is. And the equinox, of course, is the time when the sun is directly over the equator. In this instance, the sun is moving northwards over the equator, so that the northern hemisphere is moving towards summer and the southern hemisphere is moving towards winter. And the equinox is the day when we get roughly equal hours of darkness and daylight. And, of course, we get two equinoxes, one when the sun is moving towards the north over the equator and one 6 months later when it's moving out of the south. So this one in March, for us in the southern hemisphere, it indicates that winter's on its way, while our friends in the north, they've got summer coming along and all that horrible snow and stuff is going to go away. And that, Stuart, is the start of March.
That's senior science writer and Sky and Telescope magazine contributor Jonathan Nally, and this is SpaceTime. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.